Good afternoon, good evening for everyone who is attending our second series of webinar on composite materials held by Saudi Arabian Society of Composite Materials, or SASCOM. The first series was given by Professor G. Lubino on October 6, 2021. So today I'm very pleased to introduce our speaker in the second seminar series of SASCOM. Here we have Professor Joel Cugnoni. He's an associate professor at the University of Applied Sciences of Yverdon-les-Bains in Switzerland. He graduated in the year of 2000 as a mechanical engineer with specialization in solid mechanics and obtained his PhD degree from EPFL Switzerland in 2004 with specialization in dynamic identification of elastic properties of composite materials. Thereafter, he worked as a postdoctoral fellow in EPFL Switzerland under the guidance of Professor Jan Botsis in the experimental characterization and fine element modeling of microelectronic solid joints. In EPFL, he then worked as a senior researcher and lecturer in fracture mechanics of composites and multi-scale modeling of complex materials. He was appointed as an associate professor in 2018 at the University of Applied Sciences of Yverdon-les-Bains, focusing on composite structures and additive manufacturing. Professor Cugnoni's presentation is titled Thin-Ply Composites Towards Lighter and Multifunctional Aerospace Composite Structures, where he will discuss about the mechanics of thin-ply composites, highlighting the advantages and drawbacks of this new class of composites. So, Professor Cugnoni, the floor is yours. You can start your presentation. Thank you.
Thank you very much, Arif. And thank you very much for inviting me first to SASCOM and Gilles Lubino also. And it's a pleasure to be here to talk about this topic of thin-ply composites. Maybe I will start with a small background about geography, and so that you can see more or less from where I'm talking today. So if we zoom in this small rectangle, there is Switzerland, a very small country. And if you zoom in again, you have my first affiliation here, EPFL in Lausanne, where I worked about 15 years with Professor Botsis in the border of a nice lake of Geneva. And then I shifted to the next lake north from that place to Yverdon-les-Bains here in the University of Applied Sciences in 2018. I moved from a relatively large university to a much smaller one. Our University of Applied Sciences is actually multiple sites. The one in Yverdon-les-Bains is about 1,600 students, mostly at the bachelor level. But the University of Applied Sciences has a lot of other sites, and totally it's about 20,000 students. Most of our students are coming from a practical background, not necessarily oriented towards research initially, but we go also to master studies and PhD, also supervised PhDs. And I'm working in the Institute of Mechanical Design and Material Technologies, where we are about 10 professors and teachers, about 30 engineers full-time. We work very closely to the industry in mechanical design, typically high-speed machines and dynamics, material characterization and non-destructive testing, and more recently, Pauline additive manufacturing, where I also contribute. And finally, in my group, so we are currently 7 engineers working. About 2/3 of our projects are with the industry. So a lot of things that are confidential that I cannot show today. But we work in the field of 3D printing of composites and automated tape layup or in-situ consolidation of thermoplastic composites, also biocomposites, and the topic of today, thin-ply composites and multifunctional structures. And also we develop design tools and optimization methods. But that's just the overview of what we are doing. But today we are focusing on this topic of thin-ply and multifunctional structures. So the presentation will be structured in the following way. So we'll have a look at what are thin-ply composites and why they are interesting. We look at their properties, mechanical properties mostly, and how we can model Thin-Ply Composites. And finally, some application. And I will finish with the extension of, let's say, what I see as an extension of this work is development of multifunctional Thin-Ply structures that can further save weight for weight critical applications. So you probably all have seen this picture once in your life. It's the distribution of materials in the latest generation of aircrafts. And we can see that in the latest generation of long-range aircrafts, we have about 50% weight of composite in the structure. And with other optimization, it led to 20% reduction in fuel consumption. This is a huge step. However, this evolution took about 40 years to introduce that amount of composites in aircrafts. And the big question with the need to go to more efficient transportation systems is, can we go any further in the weight reduction of an aircraft structure or other type of flying objects, for example? And I think that Thin-Ply is part of the solutions that we can investigate to achieve that. And I will try to show you why and how. So Thin-Ply Composites, first of all, a definition. These are composites made of plies that are typically 30 to 70 micrometer thick, so way thinner than the standard ply thicknesses we can find today in the industry. Ply thickness can go down to 20 to even 15 micrometer, depending on the material. And it's made by advanced toe spreading process. So where the typically carbon fiber toes are spread very thinly to a few fiber diameter thickness, and then impregnated or stabilized to do non-crimp fabric, for example. These materials are commercially available, not necessarily widespread, but commercially available. It was first developed in Japan, in the center Fukui, but also we worked very closely in Switzerland with NTPT, North Thin-Ply Technology, which is specialized in Thin-Ply prepregs. There's also Chamarat in France and Oxeon, which are also producing Thin-Ply non-crimp fabrics or woven fabrics. So the difficulty also when ply thickness is reduced as much is if we handle it as a prepreg or a textile, it's not very stable when we handle it. So it's ideally suited to be used using automated tape layup system and robotic processes, because laying it by hand is relatively difficult. But why? Why do we want to reduce the ply thickness? The first and probably to address the most obvious one, this reason is that a thinner ply means a thinner laminate can be produced. And that's typically critical for sandwich structures, for example, in space application, where the skin thickness of a sandwich usually is over-designed. Usually the skin thickness is more designed based on the symmetry and balance conditions for the laminates, and it might not be critical in strength. So in these cases, which are very frequent, using a thinner ply means simply we can reduce the skin thickness and saving weight by a significant margin. For example, for a thin aerospace sandwich skin, we could move from about 1.2 millimeter thick skin, if we consider a quasi-isotropic laminate, down to a skin of 120 micron or even less, which means very close to paper thin skins, and still symmetric and balanced. And for another type of advantage based on the, let's say, the design flexibility of Thin-Ply, is that for a given ply thickness, for example, a load-bearing structure, which is several millimeter thick, we can have a much larger design space to optimize the laminate. So we can achieve much highly much more oriented or orthotropic laminates without compromising the symmetric and balance rules that we typically have in an aeronautic industry. And finally, and last but not least, I would say, Thin-Ply Composites offer much improved resistance to transverse cracking, and so they can be used to a much higher stress level without inducing damage. And that's probably the most interesting aspect. I will detail this a bit further in my talk. And just to see this in perspective, I would just like to present this example of an application for Thin-Ply composite structure. This is the aircraft Solar Impulse 2, which is the first solar-powered aircraft to fly around the globe. Not in one flight, but around the globe, just propelled by solar power. And it's a very large aircraft. It has a 72-meter wingspan, so it's like a Boeing 747, but it weighs like the same weight as a SUV. It is solar powered with batteries and so on. So the structure is extremely light. And it is all made of Thin-Ply composites. And the main reason to use Thin-Ply composites in this aircraft is that there's a large surface of the structure. So reducing the surface, the aerial weight is critical. For example, the main wing is made of a large wing box, a square wing box that you can see here, which is itself a sandwich panel structure. And it's not heavily loaded because of the weight of the aircraft, which is fairly low. But the design is mostly constrained by the minimum thickness of the ply that can be used for producing a balanced skin or the sandwich. So based on my own estimate, I would say that in this design, the skin thickness for a 3-ply layup could go down to 75 micrometer, so which is thinner than a sheet of paper, but made of high strength or high modulus composite carbon fiber. So without this Thin-Ply technology, this aircraft could not fly. And that's fairly simple. So that's the first justification of why. But then there's a much more interesting aspect, which is the why Thin-Ply are stronger. First of all, in most composites, the critical, the first damage occurs in the off-axis plies, usually by transverse cracking, as you can see here. This transverse cracking occurs around 0.3 to 0.5, sometimes 0.7% strain. However, when you look at the on-axis plies, we can use fibers that have an elongation up to 2% strain. So this means that a composite is only safe to be used for a fraction of the maximum strain of the fibers that are used. And that's a pity because we are paying a high cost for high performance fibers, but we are only using about 1/3 of this range of loading that we could use normally. In regular composites, what we have is after transverse cracking, we have generally matrix cracking induced delamination, and then at a certain point fiber failure. The use of reduced Ply-thickness has been shown to reduce the onset of free-edge transverse cracking and delamination. And this effect has been described very, let's say, very clearly by the work of Dvorak and Camagno in 2006, where it was proposed to consider that the strength of a ply is not of a transverse ply, so the transverse strength of a ply is not an intrinsic property, but it is an in-situ property. It depends on the neighboring ply. Indeed, the strength of a ply is governed by the nucleation and propagation of a transverse crack, like you see here. And this transverse crack is pinned at the two extremities by the neighboring plies. And due to this, we can see that based on fraction mechanics concept, we could derive that the effective strength of a ply in situ in transverse loading is a function of the toughness of the composite in the longitudinal intralaminar cracking and the ply thickness that appears here. So we can see here that the strength of a transverse ply scales theoretically with 1/square root of the ply thickness. And this has been demonstrated in many papers, and we also observed it. But maybe to highlight what it looks like, here are a few videos. When you can see here the free edge of a quasi-isotropic specimen during testing. Here a thick ply laminate where the 0° ply is in the center, and the 90 is here. So you can see at about 1/3, one half of the test, we have transverse cracks that very quickly migrate into delamination. And finally, a lot of delamination. And at the end of the test, only the 0° ply remains loaded. All the other plies are let's say, fragmented. For an intermediate ply thickness, so 134 micrometer per ply, we can see that most of the test there's not much happening. And here at about 50% of the test, we have the appearance of the first transverse cracks, but very limited delamination. We have a higher density of transverse cracks that develops, and finally some intralaminar cracking and delamination close to the end. And for the thinner plies, I will speed it up because not much happens. At more than 50% of the test, we still don't see any damage. Finally, we see some transverse cracks. And close to the end of the test, we see a very sharp increase in crack density of transverse crack densities, as you can see here. And all these transverse cracks, at some point, they might propagate in delamination, but we couldn't observe it. We have an explosive fracture at the end of the test. So right after this point, everything explodes. And as you can see, there's no significant delamination in this laminate. So that's a very visual way of seeing what is the effect of reducing the ply thickness. And we can also observe this through acoustic emission monitoring. If we use acoustic emission probes and monitor on the horizontal axis the acoustic energy that is emitted by the composite, and on the vertical axis the stress applied on the composite, we can observe that for thick ply laminates, quasi-isotropic, the onset of acoustic emission is about 300 megapascal applied stress, and acoustic emission raises very quickly at around 500 megapascal and stabilizes here. This corresponds to the propagation of delamination, and the first onset corresponds to the nucleation of transverse cracks. While for intermediate ply thickness, 100 micrometer plies, or thin plies like 30 microns per ply, we can observe here that the onset of acoustic emission is much higher, more than twice the value of the onset for the thick ply. And we don't have much acoustic emission before failure. So this is exactly what we have observed in the videos, but seen from the acoustic emission standpoint. If we report these different test results for different ply thicknesses, so these are quasi-isotropic laminate tensile tests. We have here in dashed line the onset of damage, so the onset of acoustic emission, and in continuous line the fracture, so the failure strength of the laminate. We can see that for the thick ply, the first onset of damage is very early, at about 1/2 of the strength of the laminate. While when we decrease the ply thickness, the onset of damage increases significantly. We reach 600 megapascal, which is actually the strength of the thick ply, and the failure strength also is increasing. By reducing the ply thickness, we have actually convergence of the onset of damage and the strength of the laminate, which means that there's no significant damage occurring before the final failure of the laminate. What is also interesting is that if we compute the strength of the laminate based on classical laminate plate theory, considering no damage and considering that failure occurs when the 0-degree ply fails, we reach exactly the values that we've tested. So this means that we can reach the theoretical strength of a laminate if we use sufficiently thin plies. While for thicker plies, the behavior is dominated by delamination and transverse cracking. For thin ply, it behaves like an homogeneous solid that is linear elastic up till until final fracture. So this is very interesting. We also verified this with many other composite formulations using aerospace grade resins and higher modulus fibers, lower modulus fibers, high strength fibers, many different kinds. And what is interesting is that in the best systems, by decreasing ply thickness, we could always reach a point where the onset of damage and the final failure are very close. And for example, here for this T800 intermediate modulus fiber with an optimized resin system, we could reach a strength for the quasi-isotropic laminate that was about 1.1 gigapascal strength, and an onset of damage which was higher than 1 gigapascal, which means a very, very high onset of damage. The onset of damage is very important because below the onset of damage, the composite is safe to be used in cyclic loading. And this onset of damage defines also the fatigue limit of the laminate. So this means that by having such a high onset of damage, this structure made of this material could sustain very high stress cycles at a stress level of 1 gigapascal, which is very, very interesting. We've collected all these results in a empirical, let's say, damage failure map or design allowable map, where you have here on the vertical axis the onset of damage strain, so the strain at onset of damage normalized by the ultimate strain of the fiber. So we have here different type of fibers, so that's why we had to normalize. And on the horizontal axis, the ply thickness normalized by the anisotropy of the ply. Actually, it was found that the anisotropy of the composite is important. So for higher modulus fiber or lower modulus fiber, there's a small effect also. So if we look here for the thick ply region, which is here around 300 micrometer plies here, the behavior is dominated by delamination, and the safe zone for use of a composite is about 30% max of the ultimate strain of the fiber. While for the intermediate ply thickness here, we have a combination of transverse cracking and matrix cracking induced delamination, and the safe zone reaches about 50% of the fiber ultimate strain. So it means we can use half of the potential of the fiber. But for the thinnest ply here, about 30 micron plies, micrometer per ply, we can reach very high values for the onset of damage, and for the best systems, nearly 100% of the potential of the fiber. This means that with thin ply, you can actually use the full potential of the fiber you paid for, which is, I think, a good sales argument, even if I'm not a salesman. If we look closer to what happens, if we look at the free edge, we can see that at the free edge, the onset of damage is not exactly the same. So the onset of free edge cracking does not correspond to the onset of acoustic emission. Actually, the first free edge cracks appear earlier than the onset of acoustic emission. To try to understand that, we did some tomography with observation point right before the onset of acoustic emission and one right after. We can see that before the acoustic emission onset, we have many small damages close to the free edges, but these are very small cracks that appear on the edge but don't propagate in the center, while we have only just a few large transverse cracks here. While just after the onset of acoustic emission, the composite is full of transverse crack and also some cracks in the 45-degree plies. So you can see that here that the onset of free edge delamination corresponds to very small crack that don't go in depth. Onset of acoustic emission really corresponds to what happens in the bulk of the material. So if we look at this graph, we can see that first we have these free edge cracks that appear. You have seen them in the video before. Then we have the acoustic emission onset with transverse cracking growth in the bulk of the laminate. And finally, we have an increase in crack density in the bulk. And finally, potential delamination, some limited delamination, and then fiber failure. By decreasing the ply thickness, we not only shift the onset of free edge crack appearance, but also we shift the onset of propagation of these transverse cracks in the bulk of the laminate. And finally, for the thinnest ply, we couldn't even observe free edge crack before the final failure of the laminate. So this is very interesting, but this difference between the free edge and bulk behavior is a bit difficult to understand. So what we did to try to analyze this is to model Thin-Ply in a multiscale manner by discretizing the microstructure of a transverse ply here with each fibers modeled from a micrography, with cohesive interfaces between the fibers and the matrix. The matrix itself is a Drucker-Plager plasticity model with damage. And the neighboring plies are modeled as continuum elements here to model the constraining effects of the neighbors. And we did this simulation with two types of conditions. One is a plane strain condition in the out of plane here, which is the condition that develops in the bulk of the laminate. And the other condition is in the plane stress condition, where we have zero normal stress, out of plane stress, which corresponds to the free edge approximately. And by running this, so we can have a look at the damage progression. So during the simulation, there's not much happening in terms of plasticity here. And then at some point we have nucleation and coalescence of small plastic damages that create cracks, transverse cracks. So if we analyze this, in the first regime of the simulation for intermediate ply thicknesses, we mostly have distributed degradation of the fiber matrix interfaces. Then we have strain localization with plastic strain that develops in preferred bands here. And these plastic strain lead to matrix damage, so degradation of the matrix, and finally coalescence of a full crack at about 1% strain. So using this model with the plane stress and plane strain assumptions, we could actually replicate properly the onset of free edge cracking and onset of bulk crack propagation here for different ply thicknesses. And this shows somehow that this is the same mechanism, but just the effect of constraint is different at the free edge by suppressing the out of plane stresses, so the out of plane constraints. Free edge cracking appears first because there's less constraints on the plasticity of the matrix at the free edge. So that explains the mechanism from the, let's say, its root cause. And finally, how to model this in terms of design. We cannot use these kind of models for design. So we used several approaches in the past, but the simplest one is just to use the principle that transverse strength of a ply in a laminate is a function of the ply thickness. So we just have to calibrate somehow what is the in-situ strength of a ply, either from a test, like we did, for example, a quasi-isotropic test with acoustic emission monitoring, And from this, we can determine what is the effective strength, transverse strength of the ply, or also in-plane shear strength of the ply as a function of the ply thickness. Then introducing this in a standard shell element with, for example, Ashin matrix failure criteria can work to predict the performance of Thin-Ply fairly well, at least until the onset of damage. Here we did simulate many different conditions, like a notch tension test, a notch open hole tensile test, and open hole compression for different laminates using simple shell theories. And we can see here that for the prediction in the thick ply, actually, the models don't match very well with the reality because a shell model does not account for delamination. And while we reduce the ply thickness, we can see that the simple shell models are actually more efficient at predicting the performance than they are more efficient for thin ply than they are for thick ply. So that's a good sign because it means that you can use classical laminate theory or shell modeling more accurately with thin ply than for thick plies, just because there's no delamination. So there's no need to change our design methods. We just have to adapt for the in-situ effect on the transverse tensile strength. So we use this in several applications. We just present one here, which was done in collaboration with RUAG and Airbus and other partners. This is the redesign of a lightweight aileron for an electric aircraft. And the focus here was to save weight and also to be fast and cheap to produce. The main idea was to avoid using a large-scale 3D mold for this aileron. So this aileron is about 2.8 meters long. It has to weigh about 3 kilograms. So we did a complete redesign of this aileron using the same method as I described before, so shell modeling with in-situ strength, simple in-situ strength failure criteria. And we used the flexibility of thin plies to actually control local buckling by using higher modulus fibers. By using higher modulus fibers, you can increase the local buckling limit. And also, because of thin ply, we don't have such a, let's say, a drawback of using higher modulus fiber because we don't have delamination. In general, using higher modulus fiber is limited by delamination, but here for thin ply, it's not really an issue. So by using a lot of different tricks like this, we could save the weight by even more than 30% compared to the initial design. And one of the tricks used to simplify the manufacturing was to use the flexibility of the thin plies. As the skin thickness here is very thin, in some areas it's less than 1 millimeter thick. We actually cured the skin of the outer skin of the aileron on a flat mold, and then we formed it elastically after curing on the ribs, and we use adhesive bonding and some clamps to close the aileron. And this is very interesting because it shows that you can actually use the flexibility, so the elastic flexibility of the ply to form an aileron after it has been cured. And we did check in terms of mechanical testing, and it passed all the criteria. So it's clearly a pass. So in the end, we saved 38% weight. So this is a very interesting aspect, but we can go even further because when we think about lightweight structures, we can think about UAVs or high altitude platforms or satellites. And in these structures, we have not only the structures, but we also have active components, antennas, sensors, we have monitoring elements, we have solar panels that have to distribute power to different components and so on. And for this reflection sparked the idea of why not try to merge Thin-Ply Composites with multi-material inkjet printing to produce a multifunctional structure. The main motivation is to remove wire harnesses in lightweight structures and to have all the electrical signals going through the skin of the composite. And this is not just simply as simple as integrating flexible PCB in the structure, because we don't want to affect also the strength of the structure. So we have to use a printing substrate for the traces, which is also a structural component. So we developed this concept in a recent project, where we actually 3D print using inkjet on a composite substrate, which is a very thin GFRP isotropic laminate, about 50 micron thick. Using inkjet printing, we can produce traces, and that have to be sintered to be conductive. And then this pre-cured, pre-printed circuit is integrated in a pre-preg laminate. So we introduce this as an interlayer in a pre-preg or on the top or bottom surface, as you can see here, with a thin layer of an adhesive film, an epoxy adhesive film. And finally, we can cure the composite using autoclave curing, for example. And in the end, we can integrate components using surface mount technology, typically here using conductive epoxy and some pick and place techniques. So I have a small example here, which is just, I don't know if you can see my camera, but this is a printed circuit on a very thin GFRP substrate that has been prepared to maximize the adhesion with a pre-preg. And you can see here the circuit. It's a simple LED dimmer where you have a capacitive touch sensor, and we can change the brightness of the LED. So that's a very simple physical demonstrator. But this component can then be integrated in a real structure. So the main question is when we integrate this in a structure is do we lose strength of the laminate by integrating an active layer like this? So we looked at the different failure modes. So one of the critical failure mode is the loss of electric signals, because if it's a critical signal, we cannot lose it, or we lose the aircraft or the UAV. So we did fatigue testing of printed layers in 3-point bending and also static testing in tension. We observed overall that the traces are actually stronger than the laminate that we were using. So we didn't see any degradation before the composite failure. And we have a limited sensing ability, which is so these kind of traces are not really good for sensing. They are optimized for signal transmission and power supply. Then the other failure mode could be delamination, because we introduce a pre-cured layer inside the pre-preg laminate. And so we did some DCB testing using a zebra pattern, where we have this multifunctional ply, where we have every 30 millimeter, we print a trace, and we have different trace width that we considered. And then we measured the interlaminar toughness using DCB for all these kind of specimens. So here you have the load displacement profile during the DCB test. Here you have the blue curve, which is the raw specimens. The raw specimens are not just GFRP; these are GFRP plus one layer of multifunctional ply like this, but without printing. So it's just the substrate itself. And for printed traces, we have these different curves below, and we can see that the fact that we are printing on these multifunctional plies actually decreases quite a bit the load capacity of the DCB specimen, which is linked to the reduction of the fracture toughness. Here you can see the average toughness or critical energy release rate measured for, well, I think it's 50 millimeter crack growth. For the raw specimen, we are reaching 1,400 joule per meter square, which is what we would expect for a GRFRP composite. While for the printed traces, it is much lower. It's in the range of 500 to 600 joule per square meter. This is lower because we have to sinter the silver ink. These are nanoparticles that have to be sintered at high temperature, and we have observed that it degrades slightly the epoxy and it lowers the adhesion also. And also the printed traces have shown that they are not sticking very well, so they are like weak spots in the structure. However, this critical energy release rate is still better than the typical toughness of a CFRP laminate. So it's still not, I mean, it's not really a weak point overall. To evaluate this, we did some cohesive modeling, modeling each region differently. So we have cohesive interfaces for the non-printed part and cohesive interfaces for the printed part. We played with the different parameters to identify the properties, and we could match the experiment. What is interesting is in the experiment, we have a jump, load jump, every time we reach a printed trace. And in the FE simulation, we can see the same behavior. So where we have a unstable crack growth when we reach a printed trace and a stable crack growth in between. So this is just to show what we can do. Now we are actually using this technology to develop demonstrators with industrial partners. I cannot show them here, but I hope I will be able to do so in the future. So I hope that with this presentation, I think I'm reaching the time. I will jump to the end. So I hope that with this presentation, I've shown you that using Thin-Ply can actually open the design space for lighter structures, and that also we can use very thin plies with GFRP thin plies as printing substrate to introduce multifunctional aspects in lightweight structures. I'd like to thank you for your attention, and I'm ready for your questions.
Thank you very much, Joel. Very excellent presentations.
Thank you.
We have one question here in the Q&A tab, so I will just read out. Or you can actually read it, but the question is, how do you think that the increase in production cost related to the benefit gains by this Thin-Ply composite?
Yeah, that's a very good question. The material is more expensive, obviously, but it's more expensive for different reasons. The first reason is volume of production. It means that you have to use a pre-preg line for a much longer time to produce 1 ton of material. So this leads to a cost that you cannot really reduce too much, and there's also the consumables used in the production that starts costing more than the fibers used because you have backing papers and films that are costing quite a lot of money as well. So I think thin plies have to be, let's say, used where they actually bring the benefit. For example, for a UAV or a satellite, 1 kilogram saved is a huge deal. While for a civil aircraft, saving on the weight of the seats is probably more interesting than using very expensive materials. So depends on the application, but I see that Thin-Ply will remain niche for a while, or remain for very high-end applications for a while. Then with an increase in production volume, could be more affordable. But today, I think it's about, we did some calculation with our colleagues from Thin-Ply Technology, and it was about 2 times, 3 times more expensive in the end. Because we also factored in that we were producing pre-stacked complex using an ATL, which also saves some time. Yeah, I don't know if it answers the question, but that's what I've experienced myself.
Thank you very much, Zul. So there is another question from Dr. Ahmed Wagi. So here is Thin-Ply seems to be an excellent in-plane loading. What about the out-of-plane and impact response of Thin-Ply composite?
Yeah. So I actually had some backup slide for this. So let me go very quickly. In terms of translaminar fracture, Thin-Plies are weak. So when you have a crack going through a laminate, typically in an open hole fatigue tests, for example, where crack tend to grow sideways, we have a much reduced translaminar toughness with Thin-Plies. This is something to be considered. It can be critical. It's more or less proportional. The effect is more or less proportional to ply thickness, so it's not a small effect. However, this brittleness can be let's say linked to the pull-out length during the fracture, and this pull-out length during the fracture is correlated can be actually restored using hybrid fibers. So that's the subject that we are working on now with the PhD of Guillaume Brogy in the IFICIN European project, where we use two types of fibers, one with a lower strain to fracture and another with a higher strain to fracture, in order to promote pull-out. And with this, we can restore at least partially the disadvantage that we have with Thin-Ply. It's still work in progress, but that's one way. And for transverse loading impact, we can reach fairly good impact properties and compression after impact properties with Thin-Ply. However, it has to be tuned, so we need to use interlayer toughening to reach very high values because we don't have much delamination. So we tend to have early fiber fracture, which is not a good type of failure mode to have in impact loading. So some other people, like in a group in Girona and also in Porto, they are working on hybrid ply thicknesses, where they use different ply thickness in the thickness of the laminate, so that they can localize a controlled delamination during impact in order to still have delamination, but not too much.
Excellent. All right. Gilles, do you have a question? Yeah.
Hey, Joel, good evening. How are you doing?
Hey,
good.
Hi, Gilles.
Yeah, a quick question. Very interesting presentation, Joel. Very nice to see. Quick question to highlight. On page 17, slide 17, you show this very interesting graph in which you normalize by thickness, but there is also the ratio of anisotropy in this E divided by E2, E1.
Yeah, it's this one.
Yeah, this one. So just for my understanding, to make sure I understand everything, that means if I work with carbon fibers, I go more towards the left, right? That means carbon fibers are going to be better in Thin-Plies compared to something that is more isotropic, like glass fibers or polymer fibers. So all this thing is due to the confinement effect, right? Due to the fact that with very stiff fibers, you maximize the confinement in it. So exactly. So that means if you want to really get advantage of the Thin-Ply technology, you need to go for stiff fibers.
Yeah, or you can state it also the other way around. If you want to use high modulus fibers, you really have an incentive to go to Thin-Plies.
Yeah. So that's why it justify when you were discussing about cost and everything. That means that this is not something that you can do with cheap, more isotropic fibers or things like this. Yeah. Okay.
No, I don't think it's. Let's say the benefit will be elsewhere. It would be more like, for example, when you do. More about the flexibility of the design and so on, but not really in the performance. No.
Yeah, good. Thank you, Joel. Thanks.
You're welcome.
So will there be any questions from the audience? If the audience have some questions, so you can write in the Q&A. If not, then there is a question about do you think that the brittleness of the Thin-Plies can be reduced if we are using thermoplastic matrix.
Yeah, thermoplastic. Yeah, I didn't answer that. Yes,
there's,
sorry.
there's a reflection about using thermoplastic for thin plies. So,
I have to be honest. We've never tried Thin-Ply thermoplastics. So it's to me it's an open subject for research. But for what I know with the failure mode of thermoplastic composites is they are much more sensitive to fiber matrix debonding than thermoset. And I mean, let's say in the guess mode, yeah. So it's not certain, but I think that transverse cracking will anyway happen because of fiber matrix debonding in thermoplastic composite, while in thermoset transverse cracking happens through plastic strain accumulation in the plastic band, so localization of plasticity. So probably it might be a different mechanism, but it all depends on the fiber matrix interface toughness and strength. So maybe there's something I can answer to show. There's something here. You see this gray curve here. This is a carbon epoxy system where the epoxy matrix was not toughened. So it was let's say a raw matrix without any toughener inside. And this epoxy matrix, the high temperature epoxy, it's very brittle. It doesn't have a good fiber matrix adhesion, doesn't have good ductility. And you can see that in this case, there's no ply thickness effect. I would imagine that it could happen in some thermoplastic, that it could be the same because of the weak fiber matrix interface. However, if you have a very good fiber matrix adhesion, then you'll be dominated by matrix plasticity, and then it will be back. You will restore the behavior like the one we observed. So that's my guess, but I've never tested.
Thank you very much. So, are there any questions? So let me check the Q&A tab again. Oh, it's from Ahmed again.
Yeah.
This seems to be very interesting. I'm interested in this.
James, some crap in the Thin-Ply thermoplastic, so we got the advantage of the in-situ strength of plies and some progressive failure mode. Yes. Yeah, that could be that could be a good idea to try to generate some initial damages that can dissipate some energy, if I understand well. And due to the use of Thin-Ply, there's not much available energy to grow delamination cracks. Yeah, that could be used. Actually, some work in Imperial College. I have to find the names of the authors. I forgot, but they were using introducing discontinuities in the fibers.
Sylvestre
Pino and yeah, but Lorenzo, I forgot his name. Yeah, Lorenzo. He was in our lab. Yeah, exactly.
Lorenzo Mencatelli.
Yeah, exactly. Mencatelli. They introduced discontinuities in the fibers in Thin-Ply composites to try to promote controlled pull out and maximize the energy dissipation. So it was the same. Actually, it was the same idea as we have for the pull-out control, but we are using fragmentation of the fibers, and they were using a cutting process. But there's a lot to be done by tailoring damage, and I think that's the future. Introducing control defects to tailor damage to have exactly the linear elastic and then non-linear dissipative regime that you want. I think this is a hot topic.
So do you have any more questions, Jill, or maybe Moha or audience? Okay, so that's it. So,
I think that's good. I mean, Joel, I hope soon you are going to be able to travel soon to come to visit us, right? It's just an invitation to conclude the.
I would be very happy, especially during the winter when it's too cold here. No, but we'll keep in touch. Yeah, with pleasure. And you're welcome if you're passing by Switzerland also. Don't hesitate to call.
Next year we will all come for ECCM.
Yeah, for ECCM, exactly.
Yeah, ECCM,
Yeah.
20 years.
Yeah, there's still a lot of work to organize this. I think I will have some duties at some point.
Good luck. Good luck.
Excellent. Thank you very much. It was a very pleasant opportunity to discuss this, and this time, contrary to ComTest, it worked. So I'm very happy.
That's good. Thank you so much, Joel. Thank you.
Thank you to everyone.
Thank you very much, Joel. I think it's really good for all of us to learn about Thin-Ply Composites, which is recent technology in the composite materials. So I hope you get the benefit of knowing the advantage, disadvantage of these Thin-Ply Composites. And can you show the email address that you have in the beginning? So if anyone has some questions to Professor Cugnoni.
Sorry. Yeah, this one.
Yeah, so you can reach his email address here.
Yeah.
So thank you very much.
Feel free to contact me, and I would be happy to discuss this or other topics.
Okay. Thank you very much.
Thank you very much,
Professor. Bye-bye.
Thanks a lot. Have a good day. Bye-bye. Or good evening, sorry.
Same to you.
Bye.
Thanks. Bye-bye.
Bye.
Thank you, Moha. Thank you, Joel.
Thank you, Arif.
Thank you.
Very good.
Thank you.
Interesting. Very good.
Yeah,
Very good timing. You know, it's quite efficient. Thank you very much.